All right, good morning, everybody at home. Can I get a thumbs up that you hear me and see the board okay? All right, I'm just going to jump right in, guys. We kind of left it hanging yesterday. I knew I wouldn't get much done just trying to build up all the original graphs. I hope you remember the graphs of these functions, but it's always good to review them when they're going to ask you to do all different kinds of things to them, right? So I filled in again. We had this filled in yesterday. This is the graph of cosine. I always remember cosine because it starts up at 1, and then it kind of makes like my little seagull at the coast looking graph in one period, right? So this was 1 period or 1 cycle from 0 to 2 pi. Okay, I believe I filled everything in up to the x-intercepts. And if you notice, again, with these periodic functions, they have infinitely many x-intercepts, because as long as they have one, eventually it's just going to start repeating itself. Yes, Kate, you want a copy? Yeah, absolutely. You okay, Michael? I jumped right in. Yeah. Don't worry, breathe.
I had to talk a little.
Okay, no problem.
This is all the stuff we wrote yesterday.
Yes, I just tried to fill in the bottom. But again, it'll be on the filled in notes so we can kind of jump to the examples. All right, so any type of periodic function that has one x-intercept, that's going to start repeating eventually, so it's going to have infinitely many. So the cosine crosses the x-axis at plus or minus odd integer multiples of pi over 2. So I said pi over 2 plus or minus, each x-intercept is pi units away from the next one, so times k. The y-intercept is up there at 1. Remember, the sine had a y-intercept at 0 because sine started at 0. 0, 0 was the first key point. All right, remember, the cosine function was an even function. That means it's going to have symmetry to the x-axis, right? When x goes in, y comes out. When the opposite of x goes in, the same y comes out. It has even function behavior. That was the identity. The cosine of the opposite of theta still gets you the same ratio as just cosine theta. Okay, just like the circle, if you picture up here, the circle gets cut into 4 parts by the 4 quadrants, right? So we consider the graph or the period of one cosine wave to get cut into what we call 4 main subintervals. So you have from 0 to pi over 2, those are your quadrant 1 angles. That's the first main subinterval. And then on that section, you have all of your quadrant 1 ratios, right? All the y coordinates that would have lived in quadrant 1. And then you have from pi over 2 to pi, those are your quadrant 2 angles. And then on that leg of the graph, you have all your quadrant 2 ratios, all the y coordinates that would have lived in quadrant 2. Then you have from pi to 3 pi over 2, those are all your quadrant 3 angles. And then on that leg of the graph, you have all your quadrant 3 ratios. And then from 3 pi over 2 to 2 pi, those are your quadrant 4 angles. And then on that leg of the graph, you have all your quadrant 4 ratios. So guys, if you remember, all students take calculus. The cosine function has a positive ratio in quadrant 1 and quadrant 4. It has a negative ratio in quadrant 2 and quadrant 3. So all of that still plays out exactly the same on the cosine curve. Okay? All right, so then in those 4 main subintervals, you have 5 key points. The 5 key points that we use to create its graph. 0, 1, which ended up being one of its maximum points. We have pi over 2, 0, which ended up being one of his x-intercepts. We have the point pi negative 1, which ended up being one of his minimum points. We have the point 3 pi over 2, 0, which is another one of his x-intercepts. And then you have the point 2 pi 1, which ends up being another one of his maximum values. So these are the key points that we'll always refer back to when we want to start transforming the graph and shifting it right and shifting it left and stretching it and shrinking it and all that good fun stuff. Okay? Which is what we're going to try to do today. I want you guys to be friendly with the graphing calculator as well too. So I'm just going to show you their sketches on the graphing calculator, and then we're going to move into the first 2 examples. All right, so I'm going to erase this. Don't get mad. It's going to be written on the filled-in notes on Google Classroom if you want to fill anything else in. I just want to get the board clear so I can start showing you something and then get to the first example. But everything is written on the filled-in notes. So I don't mean to make anybody nervous or feel like you didn't write something down. It'll be there. Trust me.
What are those last 2 points and the 5 key points?
The last key points will be 3 pi over 2, 0, and then 2 pi 1. It's these points. At 3 pi over 2, the x-coordinate was 0, so that's the cosine ratio. And then at 2 pi, the x-coordinate was 1, so that's the cosine ratio, 2 pi, 1.
All right, thank you.
Yep. All right, so guys, on the graphing calculator, just really quick, I already went to y equals, and then we were doing scatter plots last, so just make sure that your plots are turned off if you're going to use your graphing calculator. Just want to scroll up and hit the enter button so there's no black box behind it. I have the graph of y equals sine x showing right now, and there it is, from 0 to 10 and 0 to negative 10, and then what I would like you guys to get in the habit of doing is change your window. Guys, we said the sine wave goes from 0 to 2 pi. So make your x min and max 0 and then 2 pi, and let your counting increment be pi over 2, because that's what we were counting by. Each pi over 2 created one of those subintervals. So then you can just literally put second pi divided by 2. It's going to change it to a decimal, which is, I think, 1.57-ish. And there we go. And then I don't need my y's to go to negative 10. It only went from 1 to negative 1. So I'm going to put it, I'll go 5 to negative 5 to cut it a little bit shorter. Oh, I did X. And then that can count by 1, and now go to your graph. And guys, there's one sine wave from 0 to 2 pi, and it's perfect, okay? And then you can do the same thing with cosine, just to show you him in his original graph with the same settings. Enter graph. And there's cosine. And see how he's our seagull? He starts up at 1, he doesn't start at 0. So get used to these on the graphing calculator, because that can come in a lot of help if you start changing your window in those correct increments, those intervals that we want it to be on, counting by pi's over 2, which could change when we start transforming them. All right, here we go. So guys, what we're going to do in the next example, now they're going to want you to work on your vertical stretch, your vertical shrinks, your horizontal stretches, and your horizontal shrinks. In order to create that type of transformation, you have to multiply the function by something. But you have to realize, where is this multiplication being put? Is it on the outside of the function, and then it's multiplying the y coordinates by something and causing that vertical stretch or shrink? Or did they put that factor inside the function with x, which is now affecting the x coordinates, which will cause a horizontal stretch or shrink? All right? So just to give you the first example that we're going to work on, they're going to ask you to transform y equals 3 times the sine of x, okay? Now, if I look at the bottom of your notes really quick, I just wanted to remind you guys that if you looked at the cosine graph, it was literally the sine wave, but shifted back pi over 2 units. That's exactly where they meet up. They are off by pi over 2 units. But on each periodic showing, you can find the sine wave hidden inside of the cosine wave. You can find the cosine wave hidden inside of the sine wave. They're just off by pi over 2 units. All right? So they consider any type of transformation to the sine function, we call it a sinusoidal function or a sinusoidal function. So we can call the cosine function a sinusoidal function because it's just the sine curve transformed. All right? Now I want you to remember, the period is the number of inputs it takes for the function to repeat. So anytime you affect the inputs, the x's, you will therefore affect the period. So anytime you do something to the x's, you are automatically going to affect that period. If the amplitude depends on how high or low the graph goes, that's the y coordinate. So anytime you transform the y coordinates, you will automatically change your amplitude as well. So be careful with that. If we do something to x, it could affect the period. If we do something to y, it could affect the amplitude. All right, so now let's go. So the first graph they want you to graph is the graph of y equals 3 times sine x. Now, guys, the transformations we're going to do are just of these two kinds, where either you're going to be timesing the outside of the function by some a value, that'll affect the y's because it's on the outside of the function, or you'll be doing omega times x, which is inside the function, and that will affect our inputs, which will cause some type of horizontal stretch or shrink. All right, but we're not doing any phase shifts right now. We're not like jumping 3 to the right or 3 up or 2 left or 2 down. This is all just stretches and shrinks, okay? All right, here we go. I'm actually going to go onto a different sheet just to give myself a little bit more board space so I can hopefully make this make a little more sense. All right. They want us to graph on our own the graph of y equals 3 times sine x. Well, guys, who's the original function? That would just be the graph of y equals sine x, right? So the new transformation they want us to do is this 3. That's the new piece of the function. So the 3 is on the outside of the sine function, which means it'll only affect your y coordinates. So they want us to do 3 times all the y coordinates. Okay, well, in order to do that, let's get our 5 key points that we graphed the original sine function with. So your 5 key points. Use your unit circle if it helps. All right, the key points. At 0 radians, the sine was 0, so that was 0, 0. All right, at pi over 2, the sine was 1, so that's pi over 2, 1. We're getting the 5 original key points on the graph of sine x. All right, then we went to pi radians, and the y coordinate was 0, so that's a ratio of 0. The sine of pi is 0. Then we go to 3 pi over 2, the ratio is -1. And then we go all the way back, we're back where we started at 2 pi, the ratio is 0. Okay, so we're going to transform those 5 ordered pairs by doing this to all of the y coordinates to create the new graph. Now, time out. I also want to talk about what was the original amplitude on the sine wave. The original amp. It went how many units up and how many units down from that midline? Just 1, right? So the original amplitude was 1. Well, if we're going to change the y coordinates, that's going to change the amplitude. So what's the new amp going to be? Well, you always want a positive number, so it'll be the absolute value of whatever you times the y coordinates by. Guys, we're timesing the y's by 3. So the new amp will be the absolute value of 3 times 1, the old amp, which will be 3. So now the new amplitude is going to be 3 units. So I should be going 3 units up and 3 units down from the middle of that graph. Go ahead, Michael.
So, question about the domain again, is that what you were talking about before, the y equals sine x?
No, I'm just putting in if we're going to graph this transformation, I'm getting all of the original information for just the sine graph.
Oh, all right, and then we're just jumping to amplitude.
Now I'm just doing the original amplitude. All right, what was I'm getting us all set up to mark our x-axis. So the original period was how many units? How many units had to go by to create one sine wave? 2 pi. So the original period was 2 pi. We didn't do anything to the x-coordinates, right? So the period should not change. So the new period should still be 2 pi units. I didn't do anything to the x-coordinates that would change that. Okay, I'm just trying to do this to get you set up for ones where they do. You want to take the new period, which in this case is 2 pi, and we want to chop it into those 4 subintervals again. We want to get our counting increment. So guys, if you take your 2 pi and you chop it into fourths, right, your 4 subintervals, the 4 quadrants, who are we going to be counting by? What's 2 pi divided by 4? It's pi over 2. So we're still counting by an increment of pi over 2. That's still going to create all of our subintervals. So now we know we can mark our x-axis with pi's over 2. Go ahead, is that a raised hand?
Yes.
Go ahead, Jay.
You do 2 pi over 4.
Because I'm trying to get you set up for the ones that do affect the x's just by giving you some type of routine to follow. So once you know what your period is, you're going to create 4 subintervals to create those key points with. So take your period and chop it into fourths, your 4 subintervals. Go ahead, Mackenzie. Because that's our period. We know the period of the sine wave is 2 pi units. It takes 2 pi units to create one sine wave. That's how many inputs have to go by before it starts repeating itself, right? So Jay, you're always going to want to take your x-axis and you're going to cut it into these subintervals. So take your period and divide it by 4 into those 4 subintervals like the quadrants would do. Well, Jay, we didn't really change our period because we didn't change x. So just divide by 4 and we're still counting by pi's over 2. every pi over 2 will create a new subinterval, and every pi over 2 units, there should be a key point on our graph. Okay?
Yeah.
And again, this might make more sense when I do the next example, when all of this changes, where this is what I'm going to need you to do to figure out what you're counting by. Okay? So we're going to do 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2, and 8 pi over 2. Those are going to create our subintervals, and every one of them should make a key point. All right? All right, so here we go. In order to create the new graph, all I have to do, I'm all set up for where everything should land. All I have to do now is change the coordinates now. I have to times all the y's by 3. So take the original key point on the original sine curve and times his y coordinate by 3. Well, 0 times 3 is 0. So we're still going to have a point at 0, 0. All right? We're not changing the x-coordinates, so pi over 2 changes because that's going to be our next key point. We're ready for it. Take its y-coordinate, times it by 3. So now it's going to be pi over 2, 3. It's been vertically stretched by a factor of 3. All right, take the next key point. Pi stays the same. 0 times it by 3, it's still 0. All right, x-coordinate stays the same. Take the y-coordinate and times it by 3. So now it's negative 3. So now we have a key point at 3 pi over 2, negative 3. All right, take your y-coordinate, times it by 3, but it's still 0. So at 2 pi, I still have a key point. So guys, we've went 2 pi units, which is our period because we didn't change it, and we have created one sine wave that has been vertically stretched by a factor of 3. Well, guys, now that you've set your x-axis up by the correct counting increment, pi over 2, you can just repeat your pattern to create another cycle. So now I'm at 0. So the next point's at 3. The next point's at 0. The next point's at negative 3. And the next point is at 0. And you very quickly have created another cycle of the sine wave. And again, it is vertically stretched by a factor of 3. Okay? So that's as simple as a transformation's ever going to get. If you don't have to change the period and you don't have to change your counting increment that creates these key points and these subintervals, that's as easy as it's ever going to get. Just creating these vertical stretches or shrinks. All right, let's do one that does affect the period, okay? Oh, really quick, let's fill it in. Our domain is still what? All real angles. I can plug any angle I want into this transformed graph. My range, though, doesn't go from -1 to 1 anymore. My range goes from -3 to 3 because we've affected those y coordinates. We've stretched them bigger. My period is still who? 2 pi, because I did nothing to the x's that would change that. But my amplitude has now stretched to an amplitude of 3. I have gone 3 units up and 3 units down from that midline. It's a total of 6 units high. Cut that in half, that's 3. That's an amplitude of 3. Go ahead, Michael.
But how come the new period says pi over 2?
That's not my period. My new period is 2 pi. I took my period and cut it into 4 subintervals, so I knew my counting increment was pi over 2.
Oh, okay.
Sorry to confuse you there. Yeah, I'm not saying this is the period. The period's still 2 pi. I've taken my period, I've chopped it into fourths, so I know what my subintervals are divided up by now. I know who to count by. Every pi over 2 units will create a subinterval, and it will create a key point. Okay? All right. Let's go to the next example. Now, guys, on your homework, it's the graphing tool. All you have to do is you click on that graphing tool. Don't forget to click on the correct curve. If you're going to graph a sine function, make sure you click the sine curve. If you're going to graph a cosine curve, make sure you click the little gray box that says the cosine curve, the seagull, all right? And then you just put in your transformations, whether you want to stretch it by 3 or you want to horizontally stretch it by something. It's just buttons that you click online. So it's much easier online than doing it by hand. Okay. The first thing we want to do when we go to graph y equals 2 times the cosine of negative 3x, you don't want a negative argument, ideally, not when we're doing it by hand. If you put this into the graphing calculator, it would be fine. We don't want a negative argument. So we're going to use our even or odd properties to rewrite negative 3x as 3x. So guys, remember, the cosine of the opposite of theta was equal to the same ratio as just cosine theta. So remember, it's kind of like you pull that negative out and it either went in front or it disappeared. Being that the cosine function is even, I can rewrite this as y equals, if it was an odd function, I would pull it out and put it in front, and it would be negative 2 times the cosine of 3x. But this is an even function. So when you pull it out, it goes away. It's an even function. When the opposite of x goes in, the same y coordinate still comes out. So we can rewrite this as y equals 2 times the cosine of just 3x. When you take the negative out, it's still the same y coordinate coming. Somebody raised their hand.
Yeah.
Go ahead, Jay.
How do you know if it's an even or not?
We've already gone over that. We did it in the notes to day one. We saw that the cosine is an even function. We saw that when 30 degrees went in, root 3 over 2 came out. When negative 30 went in, we still got root 3 over 2, the same y coordinate. Cosine is even. Okay, here we go. So the original graph would have been just y equals cosine x, right? They want us to do this 2 on the outside, affects the y's. So that's going to be 2 times our y's. Then they put this 3 times x on the inside. Well, remember, whatever happens to x has the opposite effect on its graph. So if it says to take the x's and times it by 3, remember, the opposite of that is actually happening. The x's that make the original y's come out have just been cut into thirds. So you can think of it as the x's are being divided by 3, or I think even easier is take the x's and times them by 1/3. It's the same thing as dividing it by 3. Okay? All right, let's get our key points. What were the key points on the original graph of cosine? All right, well, at 0, it had a ratio of 1, because that's the x coordinate. At pi over 2, it had a ratio of 0. At pi, it had a ratio of negative 1. At 3 pi over 2, it had a ratio of 0. And at 2 pi, it had a ratio of 1. We're back to where we started. So those are the 5 original key points on this cosine wave. All right, let's get the original amp and the original period. What was the original amplitude of the cosine curve? 1 unit, right? 1 up and 1 down from that midline. What's the new amp going to be if you're timesing all of your y coordinates by 2? The new amp will be the absolute value of whatever you timesed your y's by, which in this case is 2, times 1, the original amp. Now the new amp is 2. So now it should go 2 units up and 2 units down from that midline.
Is the amplitude always going to be 1?
It's the original amp is always 1.
Okay.
The original amp, that's the original amp on cosine. It went 1 up and 1 down.
Okay.
Yep.
And it's the same for sine.
Yep. And the period is always 2 pi originally.
Okay.
All right. The original period is 2 pi. But what's the new period going to be? Okay. The original period was 2 pi. Now I'm taking all of my x's and dividing them by 3. So now I have to take my period and divide it by 3 as well. So my new period will be the original period, 2 pi, divided by 3. And that does not reduce. So your new period is 2 pi over 3. So guys, that means it's not going to take 2 pi units to create one cosine wave. It's only going to take 2 pi over 3 units to create one cosine wave. So picture this. From 0 to 2 pi, there used to be one cosine wave. We've just taken that 2 pi and we've cut it into thirds. So now it'll have one cosine wave in each one of those 2 pi over 3 units. we should be able to fit 3 cosine waves in the original period now. We've chopped the original period into thirds. It doesn't take as many units to create a cosine wave anymore. Okay? All right, well, if that's the case, if our new period is only 2 pi over 3 units, where do all of our key points land? Where do all of our subintervals go? So you want to take your period, 2 pi over 3, and you want to divide it by 4. You want to cut it into 4 subintervals. I need to know what my new counting increment is going to be. Well, guys, instead of dividing it by 4, let's times it by a 4th. That's easier. Because again, we need our subintervals. We need to know how often is a key point going to be created. And it's every 4th, right? So now it's going to reduce to pi over 6. So that means you want your x's to be counting by units of pi over 6. Okay, now what I would usually just have you guys do is just count 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6. But I want you to see the transformation. So let me go to 2 pi, right? This was pi over 2. This was pi, 3 pi over 2, and 2 pi. Let me just show it to you like this. Otherwise, I would literally just count by pi's over 6. So here's 1 pi over 6. Here's 2 pi over 6, which reduces to pi over 3. Here's 3 pi over 6, which reduces to pi over 2. Here's 4 pi over 6, which reduces to 2 pi over 3. Here's 5 pi over 6. Here's 6 pi over 6, which is pi. Here's 7 pi over 6. Here's 8 pi over 6, which reduces to 4 pi over 3. Here's 9 pi over 6, which reduces to 3 pi over 2. Here's 10 pi over 6, which reduces to 5 pi over 3. Here's 11 pi over 6, which reduces to nothing, 11 pi over 6. And there's 12 pi's over 6, 2 pi. I want you to see the transformation. Okay, so now we're ready. Everything's cut into the subintervals. We're ready to go. So guys, start changing your coordinates now. Take your x's and times them by a third, which is still 0. Take your y and times it by 2. So 0, 2. Got it.
Can I go to the board taking photos?
Yep. All right, take pi over 2, times it by a third. What's pi over 2 times 1/3? Guys, that's pi over 6. That's our counting increment. Our next key point is pi over 6 away. Take 0, times it by 2. So pi over 6, 0. All right, take your x coordinate and times it by a third. That's pi over 3. Because your next key point is pi over 6 away. Now we're at 2 pi over 6. We're at pi over 3. Take your y coordinate, times it by -2. So now we're at pi over 3, which we're ready for, -2. All right, take 3 pi over 2 and times it by 1/3. That's pi over 2. And then take 0 and times it by 2. So now we're at pi over 2, 0. And we're ready for it because we have the correct counting increment. All right, take 2 pi and divide it by 3. That's 2 pi over 3. Guys, that's one period. Our period is 2 pi over 3. We're at the end. We should create one cosine wave. Take 1, times it by 2. So there it is, guys. We have created one cosine wave, but it only took from 0 to 2 pi over 3. It doesn't take 2 pi units anymore because our period has been shrunk because we are horizontally shrinking this graph. And then we can just do the pattern. The next one is 0. The next one is -2, 0, and 2. And we've created yet another cosine wave. All right, then we're going 0, -2, 0, and 2. And we've created yet another cosine wave. So you see, from 0 to 2 pi, guys, it gets 3 cosine waves now because you've literally taken your period and you've chopped it into thirds. So now it takes a third of what it used to create one cosine wave. So we will fit 3 times as many cosine waves in the original period. All right, now again, in the future, guys, I would just label 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7, once you know your increment. I just wanted you guys to see how it really does shrink it in the original period, okay? All right, so our domain is still all real numbers. Our range is -2 to 2. Our period is 2 pi over 3. And our amplitude is 2. Okay, now, I think I'm going to use tomorrow. I might go over a few homework problems, but I did create a homework for tonight if you wanted to get started, but I didn't make it due till Thursday, so if I do anything in class tomorrow that helps with that, you'll still have time to correct anything or go back and finish. So it's not due till Thursday. We have time for me to go over more stuff tomorrow in class. Yes, Michael?
I'm not gonna be in this classroom tomorrow.
Okay.
I'm still gonna be here, but, I'm doing this thing called Theater Fest.
Yeah, I heard. Yeah, it's Mr. Reynolds doing it too.
Oh, I'd be there too.
That's fine.
Yeah, what would I be missing?
Either I may just do a few homework problems, a few more of these, just to kind of get you guys feeling a little bit better. And then we can, maybe that's it. I might just do a few homework problems.
Oh, all right.
Okay? All right? Sorry, guys at home. Bye, guys. Have a great day. You guys are good to go. Let me know if you have any questions.
I have a question.
Yeah, Jay, I'm ready.
For the coordinate, 3 power 2 over 0.
Yes.
No, like there on the left side, bottom left.
Yep.
Yeah, it turns into pi over 2 and 0, doesn't it?
Yeah. Oh, I'm sorry, Jay. Thank you for correcting me.
Okay.
Sorry about
That's
that.
it.
Sorry, but I'm glad you asked. Okay?
Okay, that's it.
Me just going too fast. Sorry, guys.